Hello, dear students. Welcome back to Functional Studies 101 on YouTube. Today we have an interesting problem that we are going to see how to solve, you know, this function. Analyze this function right from its domain, yes, right from its domain to the sketch. So the question is asking us to study this function and sketch its graph. Please, if you are new to this channel, kindly hit the subscribe button and don't forget to turn on the notification bell so that whenever new contents are made available on this channel, you will not be left out. And also, I will advise you to work alongside with a piece of paper and a pen so that whatever activity I'm asking you to do or I'm doing here, you'll be writing it down to follow up. This is mathematics. It is not a lecture-based text that you just read and you say you have comprehend, you have understand everything there. No, you have to write down something. Even if it's a literature class, you need to write down something. Because just hearing it is not enough. It's not enough as a student. We have experienced that. So now, without wasting much of your time, can we get into the problems proper? Like I said, this lesson is more of like a lecture. This tutorial is more of like a lecture because we are going to see how to sketch this function. We'll study the function right from its domain. Then now combine all those elements to come out with the shape of the graph, the sketch. So let's get started. All right, students, here we have I will list down the sub questions that will enable us to sketch that function. Okay, like I said, I prepared this video so that it will be easy for you to understand how to study other functions. So the first question is giving us the real value function f is defined on R, the set of real numbers, by f of x equals to x squared minus 1 divided by x squared minus 4. When we say like this, it means that when we say it is defined on R, the set of real numbers, okay? So the values of this function can only be what? Real numbers, not complex numbers. That's what it means whenever the input is x. So the first question says we should state the domain of definition of the function of representative curve CF. Okay, CF is a representative curve of the function f. We have to state the domain of that function, the f. Roman numeral 2 says we should show that f of x can be written in the form a plus b divided by x minus 2 or multiplied by x plus 2, where a and b are constants to be determined. Roman numeral 3 says evaluate the limits at the bounds of the domain and hence state the equations of the asymptotes of the function f of x. Fourth question says we should study the differentiability of f and find f prime of x, stating and determining the nature of any stationary point, if any. Point 5 says find f, the second derivative, and show that there are no points of inflection. Number 6 says find all the intercepts. Study the concavity of f and draw the table of variation. Finally, sketch the curve CF on the autonomous reference frame OIG. So this is the questions that will answer, that will enable us to sketch that graph. Okay, Yes, I particularly prepared this so that you can use it to sketch any other function of any nature. Okay, yes, because these are all the elements you need to draw simple sketches like that. For sketches with some form of oblique asymptote, I will show you how to do that one, but not in this video. So these are the questions we'll answer. So I would like us to begin with the very first one, Roman numeral 1. So Roman numeral 1, we have to do what? We have to state a domain of definition of f. Now recall this function you are seeing here, okay? This function you are seeing here is a rational function, and every rational function is defined. When they ask you to state the domain of definition, they are looking for the set of values of the independent variable x in this case, for which the function is defined. Okay, now we know that any value of x for rational functions to be defined, for instance, the denominator should never be equal to 0. Okay, we know that the denominator should never be equal to 0, so x squared minus 4 should be different from 0. From here, we know that if this 4 can be written as 2 squared, and you'll be having x squared minus 2 squared, which is now the difference of 2 squared. In other words, we are saying that x minus 2 into x plus 2 is all different to 0 by the difference of 2 square identity. From here, if the product, we know that the product of two things can only be 0 if at least one of them is 0. So for it to be different from 0, both quantities should be different from 0. That's to say that when you equate this to 0, you have x equals to 2. X should be different from minus 2, and x should also be different from 2. When you equate this to 0, what value of x will change this to 0? 2. What value will change this to 0? Minus 2. So x should be different from minus 2 and 2. So finally, we are saying that our domain of definition is the set. Remember, elements of the set are written in curly brackets. X is such that x is a real number, which is different to what? When you see a backslash like this and then some entries written in it, it means that that function is defined for all real numbers different to all real numbers x different to what? -2 and 2. All the elements. This is because these values would make this denominator to be 0. Okay, so the function will not be defined at those 2 points. That's why we exclude it. In other ways of writing the domain is to list all the points where on the number line indicate these points. In interval notation, we'll have something like this. So we'll have our number line there. Let's indicate the 2 points, -2, -2, and +2 there. And then looking at this, okay, there are intervals that you can see. This interval here, okay. After writing down this on the number line, you can see 3 intervals. Values which are less, anything that is to the left of -2 is less than -2. So we have values which are less than -2, right? That's x is starting from -infinity to -2 to the left of -2. 2 is not inclusive. Okay, here we have values between 2 and 2 without including the 2's. Okay, so we'll be using what? If you want to write this domain in interval notation, we'll be using open intervals, because these points, they are not inclusive, and the infinity we know is not a number, we don't include it. So in interval notation, we'll have something like this: domain, the set of real numbers such that x is an element of the first interval. The first interval is what? values from negative infinity to negative 2 without including the extremities, as you can see. And then now union values between 2 and negative 2 and 2. As you can see, this zone, that's it here. You have to use open. If you use this, you know it is open bracket. Another form, somebody might use this one like this. They are all accepted, please. Then now union, the last interval is this zone where x is what, greater than 2. Anything to the right of 2 is greater than 2 on the number line. So from 2 not inclusive to what, positive infinity. That's another way you can write the domain. Anyone, if you write this one is okay, write this one is okay. If you use the square bracket form where you have open bracket like this, is all accepted. Okay, so that's the domain of definition of f. Hope you understand. If you don't understand anything, feel free to write in the comment section. And if you need more videos on how to evaluate domain of various kinds of function, you can request for it and I'll create the video for you. So after studying the domain, we are asked to show that f of x is equals to a plus b divided by x minus 2 times x plus 2. So our Roman numeral 2, we are asked to show that f of x equals to this and determine a and b, right, according to the equation. So looking at this, what do we notice here? What do we notice here? That s squared, there is the same s squared down here. This is a constant, this another constant. We can write this constant, -1, as a function of -4. That's -1 is the same as what? -4 plus 3 now. Yes, so we want to create this term up there. So we can write the numerator as s squared minus 4 plus 3. This is still -1 divided by s squared minus 4. You see that we have created this term. So they are now similar. We split the fraction into 2. We have s squared minus 4 divided by s squared minus 4 plus 3 divided by x squared minus 4. From here, the ones can cancel out. Okay, this one will cancel out. Anything divided by itself is 1, right? Except 0 over 0, which is indeterminate. So finally, we have this one. This 1 plus this thing 3 on x squared minus 4. So this is f of x. But we notice that is the difference of 2 squared, which can be written as, you can write it as 1 into 3 divided by x minus 2 times x plus 2. This is a difference of 2 squares. Okay, so recall, so from this identity, if you compare with this, we see that our a is 1 and our b is 3. So that's all for this part. We'll use it later on. So we are asked to evaluate the limits and the boundaries of the domain and hence determine the equation of the asymptotes. So we know our domain, when they ask you the boundaries of the domain, they are talking of the extreme ends of those intervals. So that's why I gave you the interval notation, so that you will not be lost. Okay, so that you will not be lost. So when they ask you to give the domain of the limits at the boundaries, they are talking about the limits at the extreme points. We had negative infinity, -2 to the left, -2 to the right. Okay, so the first thing we know our function is that, I'll write it down there. Okay, so this is the other form. I'll just copy down what we just proved in the other part. So the first thing, when we have the limits at the boundaries of the domain, remember the domain we had -2. That's why I asked you to follow up with a piece of paper. If you have forgotten the domain, copy it down. You have, you know, the domain of definition was from negative infinity, then the first interval from negative infinity to -2. That's -2 to the left, values which are less than -2, right? So let's start with those two endpoints first and evaluate. So the limit as s tends to negative infinity of the function f of x, that's the first bound. the lowest bound on the number line is equals to what? Looking at this function, okay, looking at this function, when you're evaluating limit at infinity of rational function like this, for polynomials at the numerator and denominator, you consider only, okay, only the term that has the highest power of x. The term that has the highest power of x here is just x squared. If there was a coefficient, you read it alongside. So it's x squared, and you consider only the term that has the highest power of x for polynomials at the denominator. So we have x squared divided by x squared, which is 1. Okay, it's 1. In another way, you can read from here. When x gets very large negatively, that's x tends to negative infinity, if you want to use this form, you know that this denominator will get very, very large, okay? And when you are dividing by a very large number, the number is almost 0. It turns to 0. So f of s will be turning to 1. Are you seeing that? So a smart student can use this canonical form to get the same limits. So that's the first limit at the bound. The next limit now is limit as x tends to negative 2 from the left, where you write negative 2 raised to the power minus 1. Just minus with a minus sign like that. It shows that it is limit from the left. That's the notation. You can put less than there. It's also accepted in some books. The limit as x tends to negative 2 from the left of f of x is equals to what? Look up. We know that the function is not defined at negative 2, okay? Whenever a function is not defined at a point, okay? Whenever a function is not defined at a point, look up. X is the independent variable. The function is not defined at that value, x equals to minus 2. So it means that this denominator will get very small, because as x tends to negative 2, this denominator is getting what? Very, very small, okay? S is tending to negative 2. This result is approaching 0. And when you divide by a number that is very small, the answer is a very large number. Hope you understand it. So it means that what? At this point, the function is tending to what? A very large number. Then I want to check the sign. Okay, this is how you evaluate it. At a point where the function is not defined for rational function like this, when you are evaluating limit at a point where the function is not defined, you just have to know that the answer will be either positive or negative infinity. I hope you can see it. When s is tending to negative 2 from the left, when they say negative 2 from the left, it means a value that is greater than, that's less than negative 2, but not very far from negative 2. That's the limit. So if I take, for instance, negative 2.1, and I square it, it will be 4 point something minus 4. It will be 0 point something. And when you divide this quantity up divided by 0 point something, the number will be very large. But now we care about the sign, whether it will be positive or negative. That's to say it will be positive or negative infinity. Okay, now let's test the sign. When we take negative 2.1, okay, negative 2.1, when you square it here, when you square negative 2.1 is 4 point something. Okay, so let me just do that. Negative 2.1, you know, when you square any negative number, the answer is always positive. So 2.1 square is equals to what? Is 4.41. It's always greater than 1, so the numerator is positive. Then now 4.41 minus 4 is equals to what? It's positive now, because this value here is greater, so it's positive. Positive divided by positive is positive, so the answer will be what? Positive infinity, or just infinity. I hope you're understanding how we evaluate limit at the point where the function is not defined. So the next bound is now limit to the right of negative 2. Remember, we have a point on the x-axis, okay, on the number line. There is a region which is less than that point, and there is always a region which is greater than that point. So limit as x tends to negative 2 from the right now of f of x, which means we should take a value which is greater than Negative 2, but not very far from negative 2. Negative 1.9 is greater than negative 2. So we can use that. For instance, take a value not far from that point, negative 1.9 for instance. Let's try with that. So when you take negative 1.9, when you square it, you will have 3.61. okay, 3.61. So now from that 3.61, you notice that it is what? When you put it here, it will be positive. 3.61 minus 1, the answer will be positive up. But 3.61 minus 4, it will be negative down. A positive value divided by a negative value is what? A negative value. Since it is what? The function is not defined at negative 2 again, it means that this value will be getting very large when they approach that point, because this denominator will be getting smaller and smaller. And when you divide by a more smaller value, the answer is always a large number. We know the sign already, it is negative, as we have tested, negative infinity. I hope you're understanding how we evaluate limit at the bounds. The next point we had on the number line was what? 2, at the point 2. So we have the left of 2 and the right of 2. We have to evaluate that. So limit as x tends to 2 from the left of f of x will be equal to what? It means I take a value less than 2. Anything to the left of 2 is less than 2, so we can take 1.9. So take a value that is very close to 2 from the left. 1.9 is okay. So 1.9 square is exactly the 3.61. So the same scenario, same behavior, just like this one, it will also be negative infinity, because where it tests here will be positive and a negative down. So the answer will be what? Negative infinity. There is negative infinity there, sorry, I'll correct that. Then now the limit as x tends to limit as x tends to 2 from the right of f of x. From the right means we take a value greater than 2, but not far from 2. We can take 2.1. So when you take 2.1 square, you know the numerator will be positive. When you plug it in, the answer will always be positive. Since the function is not defined again at that point, so it means that the answer will be either positive or negative infinity. And the overall sign when we test with 2.1, it is positive. So the answer there is positive infinity. Please, I will swap this before uploading the video. Here we have, let me just see if I can use a pen there. So here we have negative, like that, and here we have a positive. Okay, good. Hope you understand. Now these are the limit. The last one now is the limit as x tends to positive infinity of the function f of x. Same thing, since it's limit at infinity, you can just take x squared divided by x squared, because this is the highest term in x, this is the highest term in x. Okay, so x squared divided by x squared is 1. Or you can just use it here. When this x is getting large, that's the meaning. This term tends to 0, because you are dividing by a very large number. The answer is almost 0. So we will be left with 1. So f of x will approach 1. Okay, so it's approaching 1. So these are the limits at the bounds of the domain. Hope you enjoy it, and hopefully you are enjoying yourself. This video is helpful, right? Make sure you subscribe as we go along. Turn on the notification bell, most importantly, so that whenever we upload new content, you will be the first to be notified by YouTube. So let's go ahead. So the next question we asked to state what the equations of the asymptotes. Hence, whenever the word hence is used in the equation, it means that use your answer, the previous answer you get, to get the next one. So we are deducing from here, since the function, what is a vertical asymptote? It is a line in the form y equals to some constant okay, that the function approach but never touch it to infinity. So at a vertical asymptote, I mean a horizontal asymptote in this case, sorry, horizontal asymptote. For a horizontal asymptote, it is a line, a horizontal line, y equals to some constant a, where a is a real number, for which the function approach but never touch. So since we evaluate the limit at, and the limits that are gotten from infinity, right? Yes, because this line that the function approach as extends to infinity, that horizontal line, that value that you get is always a horizontal asymptote. So at a horizontal asymptote, the limit of f of x as extends to infinity is that constant. So y is equals to 1, since as x tends to infinity here is equals to 1. So our horizontal asymptote is y equals to 1. Then for the vertical asymptotes, they are just the values of x where the function tends to either positive or negative infinity. You can see here that we had negative 2 and 2. Those are the two values of x. You can see clearly, okay? So the line is s equals to negative 2 and s equals to 2. They are vertical asymptotes. We call them vertical asymptotes because they are vertical lines, okay, that the curve will approach but never touch. So the graph is tending to infinity. As we move towards that point, it is tending to infinity, but it will never touch it. We will see that on the graph, okay? Don't bother. So all I want you to know as a student or as a first timer in the course, when you take a limit at infinity, you get the horizontal asymptote. When you take a limit of a point in at the bounds of the domain, and the answer is either positive or negative infinity, then that point is what the vertical asymptote. Why limit at infinity will give you the horizontal asymptotes. Hope you understand that. So moving ahead, we are asked to study the differentiability of f and find f prime of x, stating the nature of the stationary points, if any. So look up, our function is f of x equals to x squared minus 1 divided by x squared minus 4. I will use the second form. You can also use this form. Now, when they ask us to study the differentiability of f, we know that f is a rational function, and every rational function is differentiable over its domain. That's what you write there. So f of x is a rational function, and hence it is differentiable over its domain. That's the answer. Then now, what is f prime of x? F prime, f of x equals to what? That now, when you rewrite, remember laws of indices, this thing when it goes up, the power becomes negative. Down there, the power is positive 1. So when it goes up, it becomes negative 1. I want to use what? The chain rule rather than the quotient rule in differentiating. It will give you the same answer, please. Use any one that you feel free to. So to differentiate this function, to differentiate it, f prime of x will be equals to what? When you differentiate a constant is 0. Now let's differentiate this one. 3 is just a constant, so we keep the 3 as it is. 3 remains like that. Then how do we differentiate this part? X squared minus 4 raised to the power minus 1. We notice that this is a power function. To differentiate it using the chain rule, we use the chain rule, right? Because there is a function inside. So to differentiate, you know, when you differentiate power function, you copy the power first. So we'll copy negative 1, okay? Differentiate what is inside. Are you seeing that? When you differentiate x squared minus 4, you have 2x now. So you have 2x there. And then now we reduce the power of the function by 1 according to the chain rule. So we reduce the power of the function by 1. So we become x squared minus 4 is the power what? Where negative 1 minus 1 is negative 2. So when you simplify that, this is what 3 times this 2, 6, times this negative 1, negative 6x at the numerator. Then this one, when it goes to the denominator, the power will now become positive 2. So we have negative 6x divided by x squared minus 4, or that squared. That's the derivative of f using the chain rule. You can also use the quotient rule, bottom the top. You keep the bottom constant, differentiate the top, minus top constant, differentiate the bottom, divided by bottom squared. That's the mnemonics that we always use in class. That is it. So from here, this is my function. What do we notice from here? Look up, look up. What do we notice from here? This function is always positive. Look up, the denominator is always positive no matter the value of x you take from the domain. Okay? Yes. So this function now, the sign of this f prime, the gradient function, will depend on the value of the sign of x. So when x is positive, we will be having a negative value times a positive value, which is equal to now an overall negative value. So it means that when x is positive, the f prime of x is less than 0. And when x is negative, we'll be having negative times negative. So f prime of x is positive. So that's just what I wrote down here. So f prime of x is less than 0, means it is negative when x is positive, and it is positive, that's greater than 0, when x is strictly less than 0, or x is negative, that's the meaning. We'll use this when drawing the variation table. Keep this sentence very important. So from these points, means that whenever x is greater than 0, f prime of x is negative. And you know when f prime of x is negative, it means the function is decreasing on that interval. Okay, so it means that for the region where it is increasing, x is less than 0, it means any value from the left of 0 towards negative infinity. So f of x is increasing in this zone, f prime is increasing when x is less than 0. So it means that f is increasing on the interval negative infinity 0, and then it is decreasing on this other interval when x is greater than 0, because f prime is less than 0 there, so it is negative. Keep in mind, when the gradient of a function is less than 0 on a particular interval, it means the function is what? Decreasing. And when it is greater than 0 on the interval, it means the function is increasing. So since it is less than 0 in the interval s greater than 0, it means it is increasing on it is decreasing on that interval, as you can see there. So any value from 0 towards positive infinity. So that's all what we can do for this one. We have to do what? To detect if there are any stationary points. So for the stationary point, um, for the stationary points, we notice that our f prime of x can only be 0 since it's a rational function. In this case, f prime is a rational function, so it can only be 0 only when x is what? Only when the numerator will be 0, because the denominator cannot be 0. We have already seen that for if the denominator is 0, we'll be dividing by 0, which is what? Not accepted in mathematics. So this f prime is it can be 0 only when this numerator is 0, because 0 divided by anything different from 0 now will be what? 0. So it means that x must only be 0 now, clearly from there. So when that happens, what is the function value at that point? Because we need it. Okay, because at the stationary point, f prime of x is 0. We are looking for the stationary points. A point has the x coordinate and the y coordinate. So since we have identified that there is a stationary point at the point s equals to 0, and what is f of 0? Okay, we know that 0 is found in the domain, so the function is differentiable at 0, since it's a rational function which is differentiable at any point in the domain. So what is the function value at 0? When you put 0 here, you'll be left with -1. When you put 0 here, you'll be left with -4. So -1 divided by -4 is +1 and 4. So the point P is 0, 1, 4. So that's the function value at this point. So this is a stationary point. Okay, it's the only stationary point of our function, as you can see. there's only one stationary point of this function. So now we will now test if this point is a maximum point or a negative point using the first derivative test. The first derivative test says to test if a point is a maximum or a minimum turning point, we use the gradient, the first derivative of that function, at about values about the abscissa at that point. Our abscissa in this case is x equals to 0. So we'll consider what happens to the function when x is greater than this. Take a value not far from it. So you can take 0.1 to the right, and to the left of 0 you can take negative 0.1. Okay, yes. So when x is negative 0.1, examine the sign. When x is negative 0.1, when you come and plug it in here, okay, when you put negative 0.1 here, and you also put it down here, the overall sign will be negative over negative, which is what? Positive. Okay, so the answer will be what? Positive. So f prime, I mean, sorry, we are using it here. Sorry, I'm very sorry. Look up. When x is equal to negative 0.1, what is the sign of f prime of x? We use it here. Since x, look at the statement I gave you in the other slide. We said when x is negative, what happens? This thing now become positive now. F prime is positive. So it means that f prime is what? Greater than 0 in that zone. So when we take a value of x greater than 1, our abscissa 0.1 to the right, we know that x is positive, so f prime of x, this thing now will change to what? Negative. F prime of x is negative. So the function changes sign as we move from the left to the right about the abscissa x equal to 0. It changes sign from positive, greater than 0 means it's positive, from positive to negative. Whenever a function changes sign from positive to negative, okay, that means it is increasing. There at the stationary point, it goes horizontal, then it decreases. So whenever that happens, it means that what? It means, look up, this is what I'm saying. So the function is like this. There is a certain 0 there, okay? This is a point 0. So to the left of that 0, the function is increasing like that. Oh, let me erase that. Don't mind it, I'm using the mouse. So the function increases when it is greater. At the turning point, it goes horizontal, and then now after that turning point, it drops. That's what we are examining here. So whenever a function behaves, the gradient is positive here, and then here it is negative. So it is positive here, so it's positive here and negative here. So you see that it is like a hill, okay? It's like a hill. At a stationary point, it goes horizontal. You understand, right? At the stationary point, it goes horizontal. So when it happens like this, you see, when it's increasing, when it's positive, it's increasing, it goes horizontal, then it decreases. I'm just illustrating what is happening so that it should not be abstract to you, okay? So from this, we see that what it is what a maximum point, and since it changes value from positive to negative, it is a turning point, okay? So our stationary point P, let me just erase this. So our stationary point P is what? A local maximum turning point. If you write local maximum is accepted, you write maximum turning point is still accepted. Okay, P is a stationary point, which is what? A local maximum turning point. Hope you understand that if it was from negative to positive, that is, it first of all drops, goes horizontal, and then increase. That's it changes sign from negative to positive. In that case, we will say the function has a local minimum turning point. Please, I'm making this video detailed so that you have all the opportunity to look at it and follow it up. Okay, this video answer almost all your questions that I want to ask, but if you have any doubt, feel free to ask in the comment section. I will reply to you. So let's go to the next slide. So the next one, we are asked to find the f prime prime of x and show that there are no points of inflection. So I'll first of all start with my f prime. We know f prime was equals to that. So our f prime prime will be equals to what? To differentiate this now, we'll use now the 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 quotient rule. Since they put a quotient of two functions, when you're applying the quotient rule, the first function at the denominator remains unchanged. So bottom constant. So first of all, draw our bar, right? So we have bottom constant. Copy everything the way you're seeing it. Differentiate the top. Where you differentiate negative 6x, you have negative 6. So we have negative 6 there, minus top constant, everything that is here at the numerator, that's the meaning of top constant. That's the quotient rule of differentiation. Okay, differentiate the bottom. When you differentiate the bottom, you know we have to apply the chain rule. So first of all, since a power function that has a quadratic inside, so copy the power first. We differentiate what is inside. Where you differentiate this inside, you have 2x, and then now you reduce the power of the function by 1 according to the chain rule. So when we reduce this 1 by 1, what do you have? You'll be left with just the power 1 here, as you can see, and then that will be divided by the denominator square. Where you square this, the power will now be 4, not 2 again, as you can see there. Then all we need to notice here is that this thing x squared minus 4 is common through for each term. So this one will cancel out. The power here will drop to 1 and here will drop to 3 when it cancels out. So we'll be left with negative 6 here, negative 6 times. So negative 6 times x squared minus 1 to the first power, because one of these has cancelled out throughout. Then now here we'll be having, when this one cancels out, you'll be left with negative times negative positive. Okay, so we'll be having a positive sign there, and then now this time this, so we'll be having what? 6x times 4x, which is now equals to 24x squared. Let's divide by the denominator, which has a power of 3 now. I hope you understand that. So it has a power of 3 now. So I have to just simplify this by expanding. So I have negative 6x squared, where expand, plus 24, right? Plus 24, negative 4 times negative 6. So negative 6x squared plus 24x squared will be negative 8. That will be positive 18x squared plus this 24 divided by the denominator. So we are asked to show that this is f prime prime. Stop there. We are asked to show that there are no points of inflection. For a point of inflection, we know that f prime prime of x is equal to 0. Okay, and we know that this function, the denominator, cannot be 0 since a rational function f prime prime of x, and the numerator, you see that it is always different to 0. No matter the value of x you put in here, the numerator can never be 0 if you try it. If you try to solve, you have a complex solution there. So we can conclude that f prime prime of x, the equation f prime prime of x equals to 0, has no solution in the domain. So it means that there are no points of inflection. I hope you're understanding. So now let's go to the last segment. We are asked to find all the points of the intercepts. Okay, so we know when they ask you to look for the intercepts of a curve that you are drawing on the orthonormal reference frame OIG, that's the XY plane, for instance, we have to know that we are drawing in 2D. Okay, 2D. We have to know that you have to look for the x-intercept, the y-intercept. So my function for the y-intercept, we know that it is occurring when x is equal to 0, right? So we now have to replace in this function, we replace x by 0. When we replace x by 0, we end up with 1/4. So it means that the point a 0, 1/4 is the y-intercept. We have already proven that this point is a maximum turning point. Okay, it's a local maximum turning point. So that's my y-intercept. Therefore, the x-intercept, it occurs when f of x takes 0. Okay, it occurs when f of x takes 0. The values of x that will make this thing to be 0, that's what we call the x-intercept. So for the x-intercept, the function is taking value of 0. So in that case, this thing, we know it can only be 0 only when the numerator x squared minus 1 is 0, since the denominator cannot be 0. So it can only be 0 only when x squared minus 1 is equal to 0. So from here, let me drink some water. Okay, from here, this is the difference of two squares. You can write it as x squared, x minus 1 times x plus 1 equals to 0. We notice here that, let's see that when you have two things which are equal to 0, it means at least one of them is 0. So either x is equals to minus 1 or x equals to 1 when you solve that. So finally, we have these 2 points with abscissa minus 1 and 1, where y value is 0. They are the x-intercepts. Hope you understand it. So the 3 intercepts to our curve, we have this point A, B, and C with the various coordinates indicated. We have to study the concavity of F. The concept of concavity has to do with what? Whether the curve opens upward or opens downward. That is what you have to know. So when a curve, when you talk of the concavity, a curve is said to be concave up if the second derivative is greater than 0 at a particular interval, and is concave down when the second derivative is less than 0. That's the concept we need to keep. So our function, the f prime prime of x equals to that. We notice that we have to study by the sign of f prime prime of x to determine the concavity according to this definition. Okay, so since the numerator is already positive for all values of x, means that the sign of f prime prime of x will depend on what happens at the denominator. Okay, at this denominator, because here is not square. If it was a square, and then we would have concluded that f is concave up everywhere. Okay, but now it is not positive. We don't know whether it's negative or positive, so we have to test what happens. And here the power is odd, so it means that what happens inside here will determine whether the sign will be positive or negative. So let's have a view of this function on the xy, that's a number line. We know that there are two solutions, -2 and 2, and you have that graph. So in this zone, the function is what? Positive here and also positive that way, and then negative here. When they say it's positive, it means it's above the x-axis. It takes positive values. We are talking positive with respect to the y-axis here. Yes, the height with respect to the height from the 0 line. This is a line y equals to 0, and everything below that line is negative. Everything above that line is positive. So it means that here it is all from -2 to the left, you see that it is above, so it's positive. Then between -2 and 2, the function is what? Below the line y equals to 0, or the x-axis. So in that case, it takes a negative value there. So looking at this, we can conclude that whenever this function here takes a negative value, the overall sign at the denominator will be negative, because when you raise a negative value by an odd power, the answer is always negative. Keep it like that. So since it will take a this function here will take a negative sign when x is negative, and will take a positive sign when x is positive. Okay, so in that case, since it will take the positive sign when x is positive, it means that x is concave up. That f prime prime will be positive when x is positive, so it will be concave when this expression here is positive. So it will be concave up in these two intervals, this and this. So f is concave up on the interval from -2 to -2 all the way to -infinity, coming like this. Okay, we exclude the extremities because the function is not first of all defined at that point. Then to the right of it, from 2 above, the sign of this expression is positive, so the overall sign here of this expression f prime prime of s will also be positive, so it will be concave up also in this interval, and in the interval to infinity, from 2 to positive infinity. Okay, and f now will be concave downward. F is concave down on this interval from -2 to 2, with the extreme points not inclusive. I hope you understand the concept of concavity from here, hopefully. So after doing all of this analysis, we have to draw the variation table. Okay, we need to draw the variation table of f. So when you ask to draw the variation table, it's just now like a summary of all what we have been doing. So we have a table like that. So our variation table will always have this nature. You have to write an x there. You will create a row, right, for x. You will create another row for f prime. That's the sign of f prime, and now the behavior of f. So you will list all the values, all the boundaries of the domain. You will list it from the smallest to the largest, inserting all the turning points that were the x values of the turning point. If you have 3 turning points, put all of them. But in this case, we just had 1. So we have -infinity there, then positive infinity to the right. Then we know that there was asymptotes, right? The vertical asymptote also indicates the function was not defined at -2 and was not also defined at +2, and there was a turning point at x equals to 0. So we indicate like that. So the function is not defined at -2 and is not also defined at 2. So we shade off those regions. The function will not exist in that region. Okay, that's why we put those dark lines. Then now at x equals to 0, the function f prime of x was what? It was taking the value of 0 now. So we indicate it there like that. Then now let's test the sign. In this zone, when x was positive, we know that f prime of x was negative now, according to the expression -6x divided by x squared minus 4 all that squared. We said that, remember the statement I said. If you cannot remember, scroll back to the video, look at it, copy it down and follow up. So when x is positive, f prime of x is always negative, and when x is negative, f prime of x is always positive. So when x is positive here like this, it takes a negative value, and here, since it's also positive in this from 2 to infinity, it's also positive. Then that negative, sorry. So down there, Since s is negative in this zone, it takes now a positive value because negative times negative will be positive. We are testing means you take a value in this interval, any value. Yes, don't be afraid. Any value can take -3, -4, anything. You test in the expression of f of x, f prime of x, and note the sign. You come and write it here. Same thing from -2 to from -0. Take a value between here and test. When x in this zone, we know that x is always negative automatically. I don't need to argue that with anybody. So since x is negative here, it means that it will take a positive value here, right? F prime of x. So we take a positive value there. So I've tested all the zones. We now have to study what happens. So in this interval, when f prime is positive, it means the function is increasing. So we increase from, when it's increasing, the L will be pointing like this. When it's decreasing, it will be pointing downward like this. So since it's increasing, it will start from a certain value down, right down. Don't come and start up because it has to go up. So what was the limit as x was tending to negative infinity? It was 1. It increases now to what? It increases to the limit as x is tending to 2. We are now, look at where we are. Look at where the laser pen is. This is now the left. We are to the left of -2, right? So the limit as s is tending to -2 from the left, it was positive infinity. Put it there. Then now in this zone, from -2 to 0, you know that there was a turning point at 0, right? So first of all, in this interval, the function is increasing, so we also start from down here. So the limit as s was tending to -2 from the left, I mean from the right now, from the right, because we are at the right of -2 now. I hope you are seeing why we're doing all those limit at the boundaries. So we'll start from negative infinity, then I will increase up to the maximum turning point. There was a turning point here, so we increase to that point 104. That was a value at 0 now, the value of f at 0. Then now from that point, it will now decrease. Since it's negative in this from 0 to 2, it decreases. The derivative gradient is negative, so it's decreasing. It decreases down to the left of 2. The limit was negative infinity, so we put a negative infinity there. And then from the right of 2 to positive infinity, the function is also decreasing. So it decreases when the limit as s tends to 2 from the right. It was what? Positive infinity now. So you put there positive infinity, and then it decreases down to what? The limit as s tends to infinity was just 1. So you put a 1 there. So that's our variation table. Hope you have learned how to draw it. I took my time to do this video so that it will be easy for you to use it and study other functions. Normally, this is a tradition. This is the best way of doing it. There's no way best than this. This is the best way of doing it. So this is a rational function. If you use this to sketch any rational function, this procedure, there is no way you cannot have the graph. Depending on the rational function now, you'll be having complex. It's a rational function with polynomials. We'll now look at a rational function where you have either a radical, not polynomial, you have a sine function, the trigonometric function, and exponential. You can use this procedure to sketch all of them. I mean all of them, and you come out, the graph will come out perfect. Okay, so that was very awesome. So the last segment of our video is to look at the graph of our curve, the representative curve. So before that, I'll insert my xy plane there so that we have it. When you want to draw the graph, you have to indicate the asymptotes. There were 2 vertical asymptotes at -2. When you want to indicate the asymptote, you put broken lines like this. Okay, broken lines. There was also an asymptote at x equals to 2. You indicate like that. and then there was a horizontal asymptote at y equals 1. So you pass through like this horizontally. Put broken lines. All the asymptotes are indicated using broken lines. From here, we'll have that we have to plot the intercepts. Okay, there were two intercepts. First of all, we have to level those lines. There were two intercepts at -1 and 1, so indicate it like that. Hope you are seeing the points. There was also a turning point here. You put it, I forgot to put a dot there, so there is a turning point there. So on this interval, from -2 to the left, the function was increases. It increases from -1, not touching, and then it goes like that. So the first graph, that's it. It's a smooth curve here. Make sure to make it smoother than me. I was using a mouse. That's why it did not come out well. But that's the shape in that interval. Then now, to the left, it decreases. That's what we said now. To the left of 2, the function was decreasing, and it decreases from positive infinity up there. To the left of, it decreases to 1. This is 1 now. Y equals 1. It decreases to 1. So it decreases like that. So we have that graph. Then now, between -2 and 2, the function turns at 0. So we'll have the shape like that. So it's a smooth curve, like I said, passing through the intercept. It rises from negative infinity. Look at your variation table. It rises from 0 to -2 to the left. It was rising. It's a curve passing through the intercept, takes a turn at the turning point. Then now from 0 to +2, 2 to the left, it was now dropping. It drops, pass through the intercept, and then now it goes down. So I hope you're understanding how this graph came about. So that's the end of the presentation. So all it remains now is for me to thank you all for your kind attention, and hopefully to see you in the next tutorial. But please, before you go, give me a thumbs up. I know you enjoyed the video. You will use it, you will ease your studies in the study of functions. Give me a thumbs up. Do me a favor, share this video, and make sure you subscribe. Please, it's very important to me as a content creator. Teaching you, preparing this material for you took me some time. It's not easy to teach using a digital software. Okay, it's not easy to teach, and it's free of charge. We are giving you this knowledge free of charge. So all we want from you is what? At least subscribe to us, turn on the notification bell. When you watch a video, you share it to others so that they can also benefit from it. Because if we are not gaining views, we will not be motivated to continue teaching you for free online. We need those views to survive as creators. The reason why this video was long is for you to understand. It's not because I really made it to be long. Understand? If I wanted to just do a show, I can do this I can display this for 3 minutes, maybe, or as a short video, and no explanation. You will not be able to understand. The explanation I gave in this video will help you a lot as a beginner. Make sure you follow it. I know you have learned some tricks. Even if you have not learned, up to you, but I believe you have learned something new that you never knew. Thank you for watching, and don't forget to send us requests, video requests, maybe topics that we want interest tutorials on, because that's basically what we're doing here from now on. Tutorial until you write your examination. Whether you're from grade 1, grade 9 to 11, and year 1, year 3, year 12 and year 13, that's lower seat and up seat. Grade 1 to grade 9 to grade 11 is from 3 to from 5. Year 12, year 13, we are talking about lower seat and advanced level. So whether you're watching this video from which part of the country. This is Temgun 48 signing off. Bye bye. See you all in the next tutorial. Again, Functional Studies 101.